Welcome back to ECE 501B. I'm entitling this section Singular Value Decomposition. That's our goal, is to talk or to introduce this theorem, Theorem 46 in the second edition of Axler on the singular value decomposition, and maybe give a little bit of background or some examples of that. The singular value decomposition, just stating that theorem, says that if we're given a linear operator t that has singular values, s sub 1, s sub 2, and remember those are positive numbers, s1 through s sub n, there exists orthonormal basis, and now we have two different sets of orthonormal basis vectors on our vector space V, such that for any or for all vectors V in our vector space V, we can rewrite this linear map of T on V equal to this first singular value S1 times the inner product of V with E1. Remember, VE1 inner product is just going to tell you how the vector V is aligned with the first basis vector E1. That just gives us a scalar, and then we'll use that product of two scalars, S1 and that inner product of V with E1, and we'll use that to then weight the second basis set of vectors, F sub 1, and we do that for each of the S's and each of the E's basis vectors and each of the F basis vectors. Let's show or prove where that's coming from. We again have singular values of our linear operator, and we know how to find those. Those are the positive square roots of the eigenvalues of t dagger t. We now have found those. We have two orthonormal basis vectors of our vector space V, and we're claiming then that we can decompose the linear map T onto V, or applying that linear map on V into this decomposition in the input direction. So V is decomposed along these basis vectors E1 through E sub n, and we're using that scaling in addition to the singular values to direct to weight the second orthonormal basis set F1 through F sub n. Let's just see where that's coming from. From corollary (14), there is a basis E1, E2 up to E sub n, such that if we took this positive square root of t dagger t as an operator and applied it to this orthonormal basis E1, that would give us then S sub I E1. It now basically, these are the eigenvectors of this positive square root of t dagger t, and the eigenvalues are these singular values S sub I, where the singular values are in fact the these scalars S sub I are in fact the singular values of the original map T. So now we have found the eigenvalues and eigenvectors of this square root of t dagger t, and we've also used those to create this relationship, or that's coming to us from corollary 714. Now let's use that basis set E1, E2 through E sub n. This is an orthonormal basis of our original vector space V. We can always write any vector in our vector space capital V. We can write any vector little v. We can decompose it into pieces or components in these terms of this orthonormal basis set E1 through E sub n. So that now we have V as this orthogonal decomposition in this basis set, which is really made up of the eigenvectors of the square root of t dagger t. Now, we can do that with any vector v. What if we apply to that equation the linear map, which is the positive square root of t dagger t? Let's apply the square root of t dagger t to each side of the above equation. If we do that, then we have the square root of t dagger t times v is equal to, and now remember what the square root of t dagger t and the inner product of v with e sub I is just a scalar. That can be then slid to the left of this operator, square root of t dagger t, and that square root of t dagger t operating on these eigenvectors gives us s sub I e1. So let's now put that in. We now have S1 with the inner product of VE1 scaling E1 plus S sub 2 VE sub 2 scaling E sub 2, etc. That's how we defined the E's and the S's plus S sub n, inner product of V with E sub n scaling E sub n. We haven't done anything that we don't already know how to do. We can also say that we've confined an isometry such that the original map T can be factored as this product of an isometry S with the positive square root of t dagger t. So now let's say, and we have seen that there is an isometry S that's this linear operator such that t is equal to the isometry S times the square root of t dagger t. So if that's the case, let's go ahead and apply S to both sides of this black equation here. So now let's apply S to each side of that earlier equation so that we now have S operating on the square root of t dagger t v. It's now equal to S applied to all of these other terms on the right-hand side. Now what we want to do is actually choose or select F1, F2, F sub n such that S E sub I is equal to F sub I for all I equal to 1 up to n. And if we do that, then remember S1 inner product with VE1, that's a scalar. The S can slide through. And that now leaves us with the left-hand side, which is just TV, is equal to S1 inner product of V with E1 F1 plus S sub 2 times the inner product of V with E2 times F sub 2, etc., plus S sub n times the inner product of V with E sub n, F sub n. And that's now our proof of the singular value decomposition. It's almost impossible to say too much about this singular value decomposition. One, it actually shows action of any operator can be written as a decomposition in one set of basis vectors, or in one basis, which that's now saying let's decompose V in the direction of the E basis vectors. Then we are actually going to scale those weightings of each of those components with our singular values, S sub I, so scaling of each component by these S sub i's, and then actually do a recomposition or use these weightings, S sub I times this inner product of V E sub I, along this other basis set of F's. So a recomposition in a different basis which are the F sub i's. So that's how we can view an operator. We can say that we can view it as this decomposition, scaling, and recomposition. And that's actually a little bit strange or weird, because we normally only use one basis with a given operator, where here we actually have two bases, one on the input. You could say that's the V decomposed on the E's, and then we have an output basis, which are the F's. Here we have an input basis and an output basis. Just like with matrix representation, of a linear map, we can sort of think of this matrix representation of T on the input basis, E1, E2, E sub n, and the output basis in the F's. Here's our input basis. And there's our output basis. And if that's the case, what does this matrix representation of this linear map look like? Now, essentially, we are taking information in the input direction, scaling it by our singular values, S1, S2. Each of these input directions are decomposing any given vector. We scale relative to the singular values, and then we recombine all of those in the output directions, F1 through F sub n. In fact, as another point, so this is our third point relative to what we could say about singular value decomposition. We have, in fact, the ability we can apply the SVD to generic linear maps, where now we're not saying these are operators, these are linear maps between some input space phi and some output space w. Where now we have a generalization of this eigenvalue analysis to maps, or now we have rectangular matrices in general versus square matrices, or a square matrix. And you probably are already saying, well, we don't have eigenvalues for a rectangular matrix, and that's true. We have no eigenvalues of a generic map. But this positive square root of t dagger t is, in fact, square. And because of that, then this positive square root of t dagger t, that does have eigenvalues. We'll make one more point, and that is, now that we have this decomposition identified in terms of operators and basis, orthonormal basis vectors, we can also view this singular value decomposition as a matrix factorization. Where now, if we viewed T as a matrix and not a linear map, we could now write that as a product of three matrices, U sigma V transpose. And if you are familiar with MATLAB, MATLAB has all sorts of functions. Well, of course, it's going to have a singular value decomposition function if I'm professing that it's such a powerful operation. So now the output of the SVD function in MATLAB applied to some matrix T will give you those three matrices, U, sigma, which I'm representing as S, and V, which is the V transpose. Let's look at an example of this. Suppose we now say that we have a matrix A. That's 1, minus 1, 0, 1. It's 0, 1, 1, 1, and it's 1, 0, 1, 2. It's pretty clear that that is of dimension 3 by 4, or we do have a rectangular matrix. And if we wanted to, we could find the transpose of A pretty easily. Now the first column is just the first row, or the first column of A transpose is the first row of A. The second column of A transpose is the second row of A. And the third column of A transpose is the third row of A. And in this particular case, the domain of A, or the input to A, needs to be a 4 vector. The codomain of A is living in R3. That's our output. And we now have that A is equal to U sigma V transpose. U, again, is a matrix that's 3 by 3, and it's made up of a set of vectors that are orthonormal. V is now a 4 by 4 matrix, and it's made up of a set of orthonormal vectors. And sigma is a diagonal matrix, but it may not be square. So we now have a diagonal matrix of singular values that is not necessarily square. And to repeat, U is 3 by 3. This diagonal matrix C, again, it could be rectangular, and it's of the dimension of the original matrix A, so it's 3 by 4. And V is now 4 by 4. If we remember what we had said about trying to find the the singular values, the singular values of an operator T were the positive square roots of the eigenvalues of T dagger T. And that says then that if we look at A dagger A, which in this, over this field of real numbers, that's A transpose A, that gives us a matrix of 2, minus 1, 1, 3, minus 1, 2, 1, 0, 1, 1, 2, 3, and 3, 0, 3, 6. So that's now our A transpose A, we can find the eigenvalues of A transpose A. Those eigenvalues are actually 3, 9, 0, and 0. It's a 4 by 4 matrix, so we would expect 4 eigenvalues. The corresponding singular values of A are now the positive square roots of the eigenvalues of A transpose A, so that we now have the eigenvalues are 3 from biggest to smallest, square root of 3 and 0. And if we wanted to, we could now say that sigma is this matrix 3, and we said that it had to be 3 rows tall, and we said it was a diagonal, so we just go down the diagonal until we run out of space, and the singular values were 3, square root of 3, and 0, but we said sigma needed to be 3 by 4. We need another column, and we'll make that by just augmenting a column of zeros. And it's traditional, or it's typical, to subdivide that sigma into the different pieces, where the leftmost upper left-hand corner is our non-zero sigma matrix. We usually label that as sigma bar, and then we could have 0 submatrices everywhere else. And again, this matrix sigma is rectangular, and it's 3 by 4. Sigma bar is 2 by 2 in this particular case, where sigma bar is now this 3, 0, 0, square root of 3. We can complete this, and maybe what I will do is try to quickly write down what the other matrices are equal to. U is now going to be a 3 by 3 matrix, and each of those columns of U need to be orthonormal, or form an orthonormal set. And I've now partitioned this into the U1, which is 3 by 2, and the U sub 2. It's compatibly dimensioned with sigma. U sub 2 is 3 by 1. U sub 2 is 3 by 1, and the span, here's where we are actually getting some good information. The span of U1 does span the range of A, the span of U sub 2 is spanning the orthogonal complement to the range of A, and V is now going to be a 4 by 4 matrix. And hopefully it's clear that these are orthonormal, but now again we had 2 non-zero singular values, so now we split V into 2 pieces, with the first piece being the length of the singular values, or the number of non-zero singular values. so that now we can say that V is made up of two submatrices, V sub 1 and V sub 2, with V1 being 4 by 2 and V sub 2 for this particular matrix is also 4 by 2. And if you looked at those matrices U and V, you will see that U times U transpose, since those columns of U are orthonormal, they produce the identity V transpose V is a 4 by 4 identity, which now allows us to say, if we write A in its factored form as U1 U sub 2 times sigma bar 0 0 0, where these matrices are all compatibly dimensioned. Now if we multiply on the right by V, look at what V transpose V does on the far right. That collapses to the identity, which now says that if we had A times the matrix V, that's now A times V1 V2, but that's now the same as U1 U2 times sigma bar 0 0 0. Or if we look at what that produces here, again, U1 will be scaled by the singular values in sigma bar. U2 is getting weighted with 0, so that we now have U1 sigma bar plus U sub 2 0. Then we have U1 0 plus U sub 2 0. Or we now have just U1 sigma bar. We're now weighting the first two columns of the matrix U by the singular values in sigma bar. Those just weight the first column and the second column, since we only had two non-zero singular values. Let me keep the last column in that matrix, decomposed matrix, and now on the left we have AV1 and AV2, where this on the right is two columns wide. This is now two columns wide, and we are 3 rows tall. And if we look, this is now 2 columns wide, and what can we say? Now we can make this association with the similar blocks in this block matrix decomposition. We can see that AV1 is in fact U1 sigma bar, which is a 3 by 2, and AV2, the columns in V2 are actually spanning the null space of A, and this 0 matrix is 3 by 2. This now says that the span of V sub 2 gives us a basis for the null space of A, and the span of V1, since it's an orthogonal, or it's orthonormal to V2, that now is spanning the orthogonal complement of the null space of A. You can take that and actually form a conclusion, or find basis vectors for the 4 fundamental subspaces of a matrix. In general, these matrices U and V in our singular value decomposition, let's say if A is equal to U sigma V transpose, they in fact provide orthonormal basis for the 4 fundamental subspaces of a matrix. And the 4 fundamental subspaces with the appropriate basis vectors are as follows. For any matrix, we can find the range of A, and if we need a basis for that range of A, that we can find by performing the singular value decomposition and pulling off the vectors in the submatrix U sub 1, and those vectors will span the range of A. We know that the way that we've now split U into U sub 1 and U sub 2, and remember that U sub 2 could be nothing, but if it is something non-zero, then the span of U sub 2 will span the orthogonal complement of the range of A. Similarly, if we look at the null space of A, we've seen in the previous example that that's spanned by the vectors, the orthonormal vectors that are in the V sub 2 submatrix, and the vectors in V1 and V sub 2 are orthogonal to one another, which says then that the orthogonal complement to the null space of A is spanned by V sub 1. So I think I will stop at that point, but this singular value decomposition is very powerful, and I don't want to make you think that it's not important. It's very important, and I would appreciate it if you would really study it and really understand it, because having a way of finding orthonormal basis vectors for these 4 fundamental subspaces of any given matrix, that's a very powerful tool.